All right, this will be our first video for the first three sections of Chapter 17. In more general, it's our video about the concept of entropy. So this chapter focuses a lot on the second law of thermodynamics, and that law explains why chemical processes tend to favor one direction. Now, one of the main objectives, especially as us as chemists, is to determine whether or not a reaction is going to occur when reactants are brought together under a specific set of conditions. If a reaction does occur, if you bring it under a specific set of conditions, it is said to be spontaneous. Now, here are some examples of some spontaneous reactions, all right? Some of them involve chemical reactions. Some of them are simple, like water running downhill, a lump of sugar dissolving, and a skier going downhill. Each of these examples goes to show that, processes that occur spontaneous in one direction under the same conditions do not spontaneously occur in the reverse direction. You would spontaneously go down a hill, but you would not spontaneously go up a hill. Water will spontaneously freeze below 0 degrees, but it won't spontaneously melt. If you change the conditions, the opposite is true, above 0 degrees. Another example would be the dispersal of gaseous molecules. If you had a container of fixed volume and you doubled that volume, your gaseous particles would spread out in terms of their shape and their energy, and they wouldn't spontaneously reverse that process. So it's spontaneous to spread out as a gas particle and spread your energy out, but not spontaneous to go in the other direction. One assumption that we can make, not correctly, but one assumption that we can initially make is that reactions are spontaneous because they decrease the energy of a system. You think of these skiers and you think, well, you have less potential energy at the bottom of the mountain than at the top of the mountain, so that's why you are going down the hill. For some reactions, that may seem to be the case. For example, the combustion of methane or the neutralization of acid with base. You can see that both of these are exothermic reactions and decrease the energy of the system. But that's not always the case for spontaneous reaction. Above 0 degrees Celsius, water spontaneously melts. Now, this is an endothermic process because it takes energy. Ammonium nitrate spontaneously dissolves in water, another endothermic process. So it's not a measure of enthalpy that drives whether a reaction is spontaneous. It's something else. In order to accurately predict the spontaneity of a reaction, we need to introduce a new thermodynamic term. This new quality is called entropy. All right? In general, entropy is a measure of randomness or disorder of a system. Entropy is described more detailed as the measure of how spread out or dispersed the energy of a system is among the different possible ways that that system can contain energy. The greater the dispersal of energy, the greater the measure of randomness of the system. Most processes involve a change in entropy, and there's a natural inclination for entropy to increase in a spontaneous reaction. It's not always the case. But you can think of it like your room right now, unless you put work into rectifying this, will never be more clean than it is right now. It will naturally become more disordered the longer you don't tend to it. As order goes up, entropy goes down. As disorder goes up, entropy goes up as well. Now, a general rule of thumb in macroscopic, measurements of entropy is that in the same substance, the solid is the most ordered phase of matter. So it has the least amount of entropy, followed by liquid, and then there is a sharp increase for gaseous samples because that is where there's the greatest separation and dispersal of energy of matter. So as you go from a more ordered system to a less ordered system, you see an increase in entropy. Now, entropy involves different microstates. Now, a distribution is the general is a grouping of similar microstates. Now, microstates are the way in which you can arrange particles. Now, we'll start with just 4 particles because we want to keep this simple. If you have 2 chambers here and you have all 4 particles in one chamber, there's only one distribution and one microstate within the distribution you can make. If you increase the dispersal of that energy or these particles to, say, 2 compartments, if you have a similar distribution where there is 1 particle in one chamber and 3 particles in the other, you have 4 possible microstates within a distribution. If you increase that distribution of microstates, where you can have 2 in each chamber, you have a combined 6 ways to organize microstates in this distribution. So as you can see, as you spread out the dispersion of arrangement of particles, you increase the number of microstates that you can have. Okay. So the probability of a state or a particular distribution depends on the number of ways or microstates in which the distribution can be achieved. Right? If you have more opportunities for disorder, you're going to have more ways to achieve certain microstates. Now, Ludwig Boltzmann showed that the entropy of a system is related to the natural log of the number of microstates. Boltzmann constant is K, which makes this relationship work. That is 1.38 times 10 to the 23rd joules over Kelvin. The larger the microstates, the greater the entropy of a system. Now, entropy can be measured. It's a state function, so it can be measured simply as the final minus the initial values for entropy of a system. And a way that you can rearrange logs, where you subtract logs, is to divide them. So this is another form of the Boltzmann equation. If you have more microstates in your final arrangement than your initial, you have positive entropy. If you have the opposite, you have negative entropy. So in general, there's a couple processes that lead to an increase in entropy. We're thinking more disorder. A phase change to a less ordered phase is going to lead to an increase in entropy. Okay. Going from more ordered, let's say this is sugar dissolving in water. Going from a more ordered crystalline solid to a more dispersed solution is going to involve an increase in entropy. Now, having a solute in solution, solute and a solvent separate and mixing in solution, the only time where there might be, more order to the system is if one of the solutes was a very highly charged metal cation and caused water to orient itself around that. But in most scenarios, it involves an increase in entropy. And for any process, an increase in temperature leads to an increase in entropy. All right, that's a general rule of thumb. If all things considered are the same, an increase in temperature involves for more dispersal of energy. 2 examples of increases in entropy are the evaporation of liquid bromine and the sublimation going from a solid to gas of iodine. Now, entropy is a state function. All right, so much like other functions that you had, state functions are only determined by the final and initial conditions. So as review, we can remember when we talked about energy or enthalpy in our first thermodynamics chapter, that if you have a state function, I'm only looking at those final conditions. Both of these hikers, if we're looking at potential energy have the same change, despite one taking a more direct route up the mountain and the other one kind of, going zigging and zagging his way up the mountain. Entropy is another state function, so you really only need to be concerned with a final and initial value of this substance. So applications of Hess's law will hold true for entropy as we have with other state functions. Standard entropy is an absolute entropy of a substance, and it's typically taken at 1 atmosphere and quoted at a value of 25 degrees Celsius, because at room temperature in 1 atmosphere is typically when we're measuring entropies of substances. So to end this video, let's go over a couple examples, and we're going to predict whether the entropy change is greater or less than 0 for each of the processes. The freezing of ethanol. Freezing of ethanol involves going from a liquid to a solid. So upon freezing, they're held more rigid and in position. This phase transition reduces the number of microstates, reduces the amount that energy is dispersed within that system, and decreases the entropy as a result. Evaporating bromine increases the number of microstates because the bromine molecules can occupy more positions. And as we know, going from a liquid to a gas state is going to involve a large increase in entropy. Okay, if you're changing states, you're going to see a larger increase than otherwise. Glucose is a non-electrolyte, so we don't have to worry about those really highly charged metal cations. We're just looking at the dispersal in solution. It leads to a greater dispersal of matter and energy, and so we expect the change in entropy to be greater than 0 for this as well. Now, the cooling process for cooling nitrogen from 80 to 20 degrees, we talked about a change in temperature always being a factor for an increase or decrease. This is decreasing temperature, so we are going to see a decrease in entropy for this process.